Good day to all of you. Myself, Dr. Arvind Sharma, Associate Professor in Physics, Government Dugar College, BKN. Today's topic: Diracs Bryant Kate vectors dual space. In M.Sc previous and in quantum mechanics, Dirac Kate vectors, Bryant Kate vectors are most important part to understand the quantum mechanics mathematics. So let us start. The quantum matrix theory can be put into compact form by making use of notations invented by Dirac. Dirac invented some kind of notations related with quantum matrix theory, which are very popular. Accordingly, each dynamical state may be represented by a certain type of vector. Each dynamical state, every dynamical state can be represented by a certain type of vector known as Kate vector, or Kate represented by the symbol like that, one like this. Okay. In order to distinguish the Kates from each other, we complete each symbol by inserting a particular letter in the middle. If there is some letter in middle, then we can distinguish between the Kate vectors. For example, Kate A denotes the Kate vector. This is Kate vector A corresponding to state A, which is equivalent to psi A. What is psi A? This is a vector Kate vector A. The Kates form a linear vector space. The Kates form a linear vector space. Any linear combination of several Kate vectors is also a Kate vector. For example, let us consider two Kates, A Kate and B Kate, and two arbitrary complex numbers. You can choose any arbitrary complex numbers: C1, C2, A1, A2, D1, D2, P1, P2, any kind of numbers you can choose. C1, C2 are two complex numbers, and linear combination Ket V equal to C1 Ket A plus C2 Ket B is a vector of Kate space. Accordingly, Kate vectors may be multiplied by complex numbers and added together to give other Kate vectors. We may perform more general linear processes with them, such as adding an infinite sequence of them. And if we have a Kate vector x depending on and labeled by a parameter x, which can take on all values in a certain range, we may integrate it with respect to x to get another Kate vector. Now, integral x1 to x2, these are the limits. Kate x dx equal to, suppose, omega, h omega. If a Kate vector may be expressed linearly in terms of certain other Kate vectors. This integration shows that if a Kate vector may be expressed linearly in terms of certain other Kate vectors, it is said to be dependent on them. A set of Kate vectors are said to be independent if one of them is expressible linearly in terms of others. It is well known in linear algebra that with every vector space, one can associate a dual vector space. Dual vector space. The vectors of dual space are called bra vectors, or simply bras, and denote in general one of them by the symbol of reverse of Kate. Okay, reverse of Kate, that is the mirror image of the symbol of Kate vector. If one wants to specify a particular one of them, a label B, say it is written in the middle, bra vector B. The two spaces bra and Kate are said to be dual to each other. If the Kate space has a finite number of dimensions, the dual space Bra space has the same number of dimensions. If the Kate space has infinite number of dimensions, the dual space has the same property. There exists one-to-one correspondence between the vectors of Bra and Kate spaces. If the Kate space has infinite number of dimensions, the dual space has the same property. There exists one-to-one correspondence between the vectors of Bra and Kate spaces. Bra and Kate, thus associated by this one-to-one correspondence, are said to be conjugate to each other and are labeled by the same indices. Thus, the Bra conjugate to Kate A is represented by the symbol as subject to conditions Kate A plus Kate B, Bra A plus Bra B, and C is multiplied by Kate A tending to C star Bra A. Understand? Where the arrows indicate the correspondence between the two spaces. Each one of the two spaces takes by itself is a linear space. The connection between dual spaces is given by defining the scalar product of a Bra vector and a Kate vector such that Bra A Kate B equal to psi A dash psi B equal to integral psi A star psi B dq. You can understand by this single equation easily, and the notation expressed double lines, vertical lines is omitted. It is convention to omit the double bar and write Bra A Kate B equal to psi A dash psi B in small bracket equal to integral psi A star psi B dq. Thus we may look upon the symbols as distinct kind of bracket. The scalar product AB, Bra A and Kate B, that is psi A comma psi B, this is known as scalar product, now appears as a complete bracket expression and a Bra vector and a Kate vector in an incomplete bracket expression. Now we have the rules that any complete bracket expression denotes number and any incomplete bracket expression denotes a vector of the Bra Kate space according to whether it contains the first and second part of bracket. The first three Bra and the last three Kate vectors of bracket provides the names for the two kinds of the state vectors. Bra and Kate, the Bra vector is analogous to the complex conjugate or Hermitian adjoint of the wave function of the system. Evidently, Bra A Kate B equal to Bra B Kate A star complex conjugate, that means this is reverse or mirror image. Bra A bracket Kate B plus Kate B dash equal to Bra A Kate B plus A Bra A Kate B dash, and you can similarly understand Bra A C multiplied by Kate B equal to C is scalar product of A and B, Bra and Kate B, where C is any number. The Bra conjugate to Kate V equal to C1 Kate A plus C2 Kate B, and its complex conjugate is Bra V equal to C1 star Bra A plus C2 star Bra B. Thus, the correspondence between the Kates and Bras is analogous to the correspondence between the wave function of the wave mechanics and their complex conjugate, just like Bra is complex conjugate of Kate vector. Again, just see this. This is the very important conclusion. Thus, the correspondence between Kates and bras is analogous to the correspondence between the wave functions of wave mechanics and their complex conjugates. We further note that if a cat vanishes, its conjugate bra also vanishes and vice versa. If a cat vanishes, then its conjugate bra also vanishes and vice versa. A bra and Kate vectors are said to be orthogonal. Bra and Kate vectors are said to be orthogonal. Okay? If their scalar product is 0 and the two bras and two Kates are said to be orthogonal, if the scalar product of one with the conjugate imaginary to other is 0, a very important point to be noted, if two Kates are orthogonal, if the scalar product of one with the conjugate imaginary of the other is 0. Further, we shall say that two states of our dynamical systems are orthogonal if the vector corresponding to these states are orthogonal. The length of a bra vector A or of its conjugate imaginary Kate vectors is defined as the square root of the possible number bra A, Kate A. If we wish to set up a bra or Kate corresponding to a given state of the system, only the direction of vector is given and the numerical value of vector is undetermined. It is convenient to choose this numerical value so that the vector is of unit length. This vector is said to be normalized, and thus the procedure is called normalization. Still, the vector is not completely determined since it can still be multiplied by any factor of unit modules like e raised to iota alpha, and alpha being real. Such a number like e raised to iota alpha is called phase vector. Such a number like e raised to iota alpha is called phase vector. Operation on the Kate from the left and operator P produces another vector. If P operate on Kate vector equal to n dash Kate, another Kate vector. And operation of any bra from the right with P produces another bra vector. Bra M P equal to bra M dash. The Schrodinger equation H psi n equal to En psi n in this situation reads H minus En. This function is replaced by Kate vector. Psi n is just Kate n equal to this. It is represented by this. Psi n represented by this vector. And the matrix H&M of this is H&M equal to integral psi n star H psi m dq equal to psi n dash H psi m. This is scalar product notation equal to bra n H and Kate m. The bra vector and the basis vectors of representation as say in the vector space R. These vectors form a complete orthogonal set. Complete orthogonal set. Bra n Kate m equal to delta n. The closure relation is expressed as, this is known as closure relation, summation Kate n bra n equal to I a unit matrix. This is known as closure relation. The change of basis from one orthonormal set to another in Dirac notation is expressed as Kate p equal to bra n Kate n bra n Kate P, because this is I, which is in old notation corresponds to psi p equal to summation n phi n un p. Thus the bracket bra n Kate P is identified with the element un p of the transformation matrix U. Further, in old notation, base vectors in different bases are distinguished by the use of different letters psi n, phi m, etc., but only different indices as arguments are employed in Diracs notation. According to expansion postulate, any arbitrary state vector may be expressed as a linear combination of base vectors psi p equal to summation n phi n. In Dirac's notation, this expansion postulate states any arbitrary kate can be expressed in terms of the base kates. Thus, if arbitrary vectors phi p equal to kate p and base phi n equal to kate n in the representation S, then in new notation, the expansion postulate reads kate p equal to bra n kate n bra n and kate p, so that each component an of arbitrary vectors psi p along direction of the axis of the base vector phi n is denoted by bra n kate p. The quantities bra n kate p may be regarded as the element of a one-column matrix whose row index is n. This column vector gives complete definition of kate p as a matrix in terms of S representation. So today in this lecture we just try to understand the bra n kate vector notations in dual space. Thanks to all of you.